Hi Year 12s. So today we'll be looking at subtopic 3.4, carbohydrates. Now carbohydrates have a specific, or used to be known for having a specific formula, and that is for every carbon that the molecule had, there would be the same number of water molecules. So we have an X value, X number here and here. They can also be written in this form here, where we have for every carbon we have the same number of oxygens and twice as many hydrogens. Now the definition has changed a little bit, and now it can be polyhydroxyaldehydes or polyhydroxyketones. Now they can be called aldose and ketose respectively as well. Now the polyhydroxyaldehydes, they have our aldehyde group, which is our C-double-bond-O with our hydrogen at the end of our molecule. And that's what makes an aldehyde, and the polyhydroxy bit is all these hydroxyl groups that are coming off that carbon chain. Now similarly, for our ketose, our polyhydroxyketones, we have a ketone, or a keto group, with our C-double-bond-O with carbons coming off of each side. Now each of those carbons in both glucose and fructose have one hydroxyl group per carbon. At least per carbon isn't directly attached to our double bond O. Now, as you can see, the first way I've represented them here are chain forms, so where you've got your carbons in a chain. But these carbohydrate molecules are actually in equilibrium with another form, which is called ring form. Now, what happens is, I'll see if I can highlight this so it's nice and clear, is this carbon here will attach with this carbon here, ending up with, where are we? Yep, here. And, oh actually, sorry, I made a mistake there, my bad. So, that carbon will attach to this oxygen over here. So we end up with this carbon here and this oxygen here. And you don't need to know the actual mechanism of how this happens, but just know that the oxygen that is within the ring was one of the OH groups, one of the hydroxyl group oxygens. And similarly, I might do a different colour just for fun. Let's go green. Similarly, in our ketone, we have our carbon that is attached to here. That will attach to that second to last carbon as well. So I'll go back a minute, just so I can highlight things, a couple other things. This group here, this OH onto a carbon, that is this same group here. So we join this to this one to this one, and actually I might as well highlight the whole thing. Why not? Highlight there and there. So that's what this carbon's for. Oh, that bit is that carbon, and then over here, similarly, this one here is going to be this one over here. Again, not super important to know exactly how they attach, although I have seen some questions where they ask you to number the carbons that are that make part, the number of carbons that join, the carbon numbers that join to make these ring forms from the chain form. So it will be good to at least understand how these join together. Again, remembering that we have the carbon that's attached to the oxygen over here will bond to the second last OH all the way around the other side. So you'll end up with this carbon involved, 1, 2, 3, 4, 5, and 6 to make our 6-membered ring. And over here we have this carbon with this one carbon, 2, 3, 4, and then the oxygen to make our 5, which is our 5-membered ring here. So once we move past these, this equilibrium of the ring form and chain form, knowing by the way that this equilibrium occurs in solution, so when these are dissolved in water, these equilibrium happen. If they are solid, so solid sugar, the crystallized sugar, they don't go through this process. Okay, so now we're down to this bit here, which is the fact that these carbohydrate molecules, or what you can also call them as monomers or monosaccharides, they can actually join up and join into bigger molecules. They can join into disaccharides, which is taking or having two monomers. They can also join into polysaccharides, which are more than 2 units. So it could be 3, it could be 4, it could be 100, or it could be 300. Doesn't really matter. One thing you do need to know though is that every time the joining of monosaccharides is called a condensation reaction, and that involves the loss of a water molecule. So condensation, it releases water when these things occur, and we'll have a look a bit further at some more detail there. Now, the last piece of information that we're going to cover in this little part is that carbohydrates are soluble in water, and the reason for that is due to their extensive hydroxyl groups. Now, these hydroxyl groups can take part in hydrogen bonding with water molecules, and what that means is if you put a molecule such as this fructose and surround it with water, the water will be happy to hydrogen bond. No, sorry, I should probably draw it more clearly. So we have our bonding between our oxygens and the hydrogens, as well as from the oxygen and the hydrogen within between the water molecule and the OH group. And because this interaction happens, which is a stabilizing interaction, that means water is happy to interact with this. It's happy to sort of move apart from each other, as in the water molecules move apart from each other, making space and dissolving those carbohydrates. If it was, if they were not having favourable interactions, then the water would prefer to bond to itself, and it would not let the carbohydrates come in between them, and that would make it insoluble. So these are soluble because of all their hydrogen bonding, or the hydroxyl groups that can form hydrogen bonds with water. Okay, so we're going to move down to the next bit, which is more about the joining of these carbohydrate monomers into disaccharides and polysaccharides. We are going to look at glucose to start with. So glucose has a formula C6H12O6. So you can see how the formula here with our six carbons and our 6 water molecules, which gives us H12O6. When we join 2 glucose molecules together, as we are illustrating here, we are going to end up losing a water molecule, which is 2 hydrogens and an oxygen. That happens by the loss of one of our OHs, one of our hydroxyl groups, and loss of the hydrogen off another of the hydroxyl group of another molecule, giving us what's called a glycosidic bond. So that, I know I've highlighted these two in red, and then I've also highlighted this oxygen in red, but it's actually this leftover blue oxygen that is this oxygen here. Now, every time these monomers join together, you are going to lose one water molecule. If we continue this polymer and made it longer and longer, each time a joint is like a glycosidic bond is formed, you'll be losing a water molecule. So when it comes to the molecular formula of this disaccharide, so this one that we've made just here, you don't actually need to count up all of the individual atoms that make it up. Instead, you can recognize that we took 2 molecules of water, so water, 2 molecules of glucose, which has this formula here. When you join them together, you're going to lose a water molecule. So if we show this as an equilibrium just down here, we have 2 C6H12O6s. If we start from that in a condensation reaction, we're going to form C12H22O11, which is our 12 carbons, our 11 water molecules, because we've lost one as well. Now I've shown the equilibrium going back the other way. Now that process where we take our disaccharide and we add water to it, so split it up, adding these OHs and the H's back, that is called hydrolysis, and that is our reverse reaction. Now, I just mentioned a second ago that the equilibrium involves the polysaccharides or the disaccharides being broken back down, and that being called hydrolysis. And that is something you will definitely need to remember. One other thing another thing you have to remember is, it's not remember, be able to do, is you'll be required to be able to identify and draw the monomers if you are given a disaccharide to start with. So, for example, if you are given this structure, you are going to be able to, you're going to need to identify the glycosidic bond, so this one here, and you're going to have to break it, adding a hydrogen back to this oxygen here to make it a hydroxyl group, and then adding an entirely new hydroxyl group back to the other one. So if we break it here, we're going to put OH onto this one and put our hydrogen back onto that one there. Cool. Now we have one little bit left, and that is you will be expected to know what to do when you are given a section of a polysaccharide. So if you're given a section of a polysaccharide, you're going to have to identify the monomers that make it up. So in this particular case, we have 3 glucose molecules, or monomers, sorry, that have been joined together to make this larger structure. And you need to identify that that this is the repeating unit. This one section here, this one piece, this monomer is the repeating unit, and you're going to have to draw it. Now, the way I've drawn it here is I've just chopped off at the glycosidic bond on both sides, made sure that those, whatever I chop off, if I chopped off here and here, either way is fine, but you're going to end up with hydroxyl groups on the ends of these carbons for both of them. So that's what I've drawn just here and here. Now, there are other little bits and pieces of information that come along with this sort of stuff, but like usual, this is meant to be a decent-ish introduction. It's not meant to give you all the little details that you'll find in the textbooks. Cool. I hope that's helpful.